Good afternoon, everyone. I am Hoa. Welcome to my presentation of my conference paper with title A Lightweight Model for Phone Detection. This paper was accepted in International Conference 2021. This is the outline of my presentation, including introduction, description of dataset, methodology, result, discussion, and conclusion. To make presentation more clearly, firstly I will talk some background about phone action. In our paper, a certain phone is defined when a person can control movement of body to lying down on the ground or floor. Phones happen anywhere with anyone at any time. Especially, it often occurs with children and elders. We can see two examples here. The children easily to fall when they play around, or one of common place where fall happen is escalator in the mall. Is it really dangerous? According to the 2021 report of WHO, fall is the second leading cause of unintentional injury deaths worldwide. Particularly, 684k people die from fall and 37.3 million fall require medical attention each year. The report also indicates that more than 60 years old people suffer the greatest number of fatal falls. This motivated us to study on fall detection. It is found that reliable and fast fall detection system can reduce the negative effects of accidents due to falls. It can help to increase the time needed for a person to receive medical care. Beyond this idea, we propose a new model with less parameters, more complex and computation, computational cost, and easily deployed in mobile or embedded device without GPU. In our paper, we will implement the model over two popular phone action datasets, phone detection dataset and University of Jesu's phone detection dataset, in which FDD was constructed in 2013 with 191 videos at cafe room and house. The resolution video in this dataset is 320 by 240 and the frame rate is 25 fps. 1 year later, Bowden et al. Built URFD dataset in the laboratory. The dataset contains 7 videos consisting of 30 phone and 40 activity of daily living. This data was created by Camera and Microsoft Kinect. In this paper, we only use videos from Camera. In our paper, we have proposed a new three-dimensional model based on MobileNet architecture. So, firstly, let me show the standard CNN process applying for phone detection in MobileNet. Give a feature map or an image whose parameter is h times w times l, in which h, w, and l are height, width, and number of channels, respectively. When when applying the standard CNN architecture with a kernel having a size of k times l, the two-dimensional output is obtained. Instead using image, the two-dimensional input data, the new model will use a video. Similar to the standard CNN, our Convey 3D in the right-hand side is used for input data of video with an extra parameter of time. When applying and filters Convey 3D with k kernel for input data whose size is t times h times w times c. The number of parameters that is needed to use is calculated by equation 1. The number of multiplication that computer need to implement when apply Convey 3D will be used equation 2. Is it clear that the number of parameters and multiplication will be used if L is large? So problem here is how to reduce this feature. Similar to mobile net, our paper uses deep-wide separable convolution as a key idea to reduce the computation in the first few layers. Deep-wide separable convolution are made up two layers including deep-wide 3D and point-wide 3D, which are built as a variant of deep-wide convolution and point-wide convolution. Deep-wide 3D will be used to apply a single filter per each input channel, and point-wide 3D is then used to create linear compilation of the outputs of the deep-wide layers. It means that instead of using the Convey 3D, our model uses two layers including deep-wide 3D and point-wide 3D convolution. The computation cost of deep-wide separable convolution is calculated using equation 3, 4, 5, and 6. Similar to Convey 3D, depth-wide 3D with k times k kernel which contains the number of parameters and multiplication as in equation 3 and 4. Point-wide 3D layout work as in Convey 3D. However, the size of kernel is only 1 times 1 times 1. Hence, the number of parameters and multiplication in this layer as in equation 5 and 6. Therefore, the number of parameters of the depth-wise separable convolution is total equation 3 and equation 5. Similarly, the number of multiplication is total of equation 4 and equation 6. Making a comparison between the total of equation 3 and equation 5 with equation 1. The reduction in computation of parameter is achieved as we can see in equation 7. Similarly, the reduction of number of multiplication SU depth-wise separable convolution is shown in equation 8. Obviously, application of depth-wise separable convolution helped to drop the computation cost of the new model. The proposed MobileNet 3D model has constructed with config parameter of each layer as in table 1 in the right hand side. Similar to the original MobileNet, all layers is model are followed by a path norm and reduce nonlinearity as we can see in the left hand side. As we have mentioned above, the experiment of our model is implemented over FDD and URFD dataset. The model have channel with Adam optimization in which the training video were divided into many clips with 16 frame length, and 16 clip each batch. Learning rate which was used is 0.001 to evaluate the model accuracy. Five-fold growth validation is due to result of model is compared with recent methods. A comparison in terms of precision, recall, and accuracy of our model and some state-of-art model over FDD dataset is shown in this table. We can see our MobileNet 3D achieve the best result in precision and accuracy factor among methods with proportion of 90.8% and 90.5%. More clearly, the precision and accuracy in mobile net 3D are 1.48% and 1.07% higher than those of three James model which have kept the highest rank among previous method work. For the calculation measurement recall, our model is 1% lower as compared with RGB and both estimate methods, and gets the same result with the remaining model. Similarly, the result of URFD dataset indicated that on criteria of model MobileNet 3D holds the first position among methods work with 1.29% and 1.13% higher compared with those the best method in the rest model. It can be seen in as comparison in terms of number of parameter and number of computation cost. The number of calculation that MobileNet 3D must perform is also much less than that of VGG16. The the ZF of previous model are 50 times as much as our model whose ZF loops is only 0.3. Strikingly, the number of parameters which were used in our model are 0.2 million, which is very small as compared with the rest one. Evidently, our model have improvement on not only the size but also the speed. And conclusion. In this paper, we propose a lightweight model based on MobileNet architecture to determine people who are falling down from the videos. Aside from the significant decrease of the number of parameters and calculation, the new model shown its efficiency as compared with recent models. Furthermore, our model could solve real-time problems. The future work could be to improve the accuracy of model and apply the model to various problems in image processing and intelligence. Strikingly, the number of parameters which were used in our model are 0.2 million, which is very small as compared with the rest one. Evidently, our model have improvement on not only the size but also the speed. And conclusion. In this paper, we propose a lightweight model based on mobile net architecture to determine people who are falling down from the videos. Aside from the significant decrease of the number of parameters and calculation, the new model shown its efficiency as compared with recent models. Furthermore, our model could solve real-time problems. The future work could be to improve the accuracy of model and apply the model to various problems in image processing and intelligence. Moreover, the datasets are used in this work uh, contain video in which actors were done by actor for action were done by actor following contextual scenarios. Reals. Moreover, the datasets that are used in this work contain video in which action were done by actor following contextual scenarios, not the real-time situation. Therefore, it is needed to consider the dataset of real situation, a data with multi-person in video and a bigger size. And then this is my references. Thank you so much for spending time to watch my presentation. If you have any question or classification, please contact me via my email. Thank you.